Hello everyone, I'm Hazim Sheikh and today I'll be presenting my research project titled Optimizing Call Center Operations Using Markov Decision Process. In this presentation, I will discuss how Markov Decision Process or MDP can be applied to enhance the performance of call centers by optimizing call routing and minimizing wait times. I'd also like to acknowledge my supervisor, Vatsala, for her invaluable support throughout this project. Let's get started. The goal of this project is to improve call center operations by optimizing the way calls are routed to agent and using a technique called Markov decision process. The main objective is to dynamically route calls in a way that reduces customer waiting times and while maximizing the utilization of available agents. So in a typical call center, call may be queued for long period of time. An agent may remain idle at times, which affects overall productivity and customer satisfaction. By applying MDP, we aim to reduce these inefficiencies by making data-driven decisions in real time. The problem we are addressing is a common one, which is inefficient call routing. This issue often results in longer waiting times for customers and unutilization of agents. It happens because calls are routed based on fixed rules without considering real-time data, leading to suboptimal resource allocation. In terms of methods, we use MDP modeling where we represent the system as a state space. Here the state is a combination of number of calls in a queue and the status of the agents, whether they are busy or idle. We then apply value iteration, a dynamic programming technique to solve this model over time and determine the optimal policies that minimize waiting times and the makes best use of available agents. Now that we have set the stage with objectives of optimizing call center operation using MDP, let me walk you through how we applied this in our previous work. Imagine a typical call center. Calls are constantly arriving and agents are there to handle them. But often, calls are waiting too long or agents are sitting idle, which results in inefficiency. We tackle this by applying Markov decision process. Here, the state of the system is a combination of the queue lengths and the status of the server, whether they are busy or idle. Our goal was to make decision based on this state, deciding which calls should be routed to which agents, or whether we should wait before making any assignments. The heart of the system is reward function, which penalizes long waiting times. Essentially, the reward becomes greater when fewer customers are waiting, which directly translate to improved performance. We use dynamic programming and simulation to solve this problem and find the optimal policy. This approach not only reduced waiting times but also ensured that agents were used efficiently. And then we saw in the result it made a real difference in performance. If you'd like to dive into the detail of the code and methodology, feel free to explore the full implementation on my GitHub repository. In this project, we model the call center as Markov decision process. The core of the MDP is state space, which includes the number of customers in each queue and the status of each server, whether they are busy or idle. The action space is defined by how we design calls to server or decide to take no action if a server is already occupied. The reward function plays a crucial role in guiding the system towards minimizing waiting times. It does this by penalizing the total number of customers waiting in the queues, ensuring that calls are routed efficiently to available server. To compute the optimal policy that minimizes waiting times, we use Bellman equation. This equation helps us calculate the best decision at each state, considering both immediate rewards and long-term outcomes. The goal is to determine the optimal action for routing calls, reducing customer wait times, and improving overall efficiency. To evaluate the effectiveness of our call routing strategy, we implemented a simulation based on our Markov decision process model. In this simulation, we simulated dynamic call routing model by Poisson process, which is commonly used to represent random call arrival in call center. The service rate for calls were modeled using exponential distribution, representing the time it takes for each server to handle call. This setup closely mimics the real-world service environment in a call center, where there are fluctuations in speed at which agents serve customers. We track several key performance metrics using the simulation queue lengths over time. This tracks how the number of call waiting in each queue changes over the course of simulation. And the second one is server utilization. This measures how much time each server spends being busy serving calls, which reflects how effectively the agents are being used. And the third one is cumulative customer serve. This tracks the total number of customers served, providing a clear view of system throughout. And the result from this metric help us assess the effectiveness of our call routing strategy and determine how well our approach reduces waiting times and maximizes this agent utilization. Let's now dive into the visual results from the simulation. In the simulation, we track several performance metrics to assess the effectiveness of our call routing strategy. First, let's look at the queue lengths over time. This graph provides a clear picture of how the queues for type 1 and type 2 calls change throughout the simulation. We can observe periods when the queues grow, signaling that calls arrivals are higher. Following this peak, we see drops in the queue length, which indicates that calls are being processed by server. Next, we have the server utilization graph. This shows how much effective each server was utilized over the course of simulation. As you can see, both servers are actively engaged throughout, reflecting an efficient use of available resources. One key takeaway from this is that high server utilization typically correlates with reduced waiting times for customers, suggesting that our model is performing well in balancing the load across available servers. Let's now look at the cumulative customer served over time graph. This visualization helps us evaluate the effectiveness of our call routing strategy by showing the total number of customers served as the time progresses. We can see that the graph indicates steady progress with occasional jumps in the number of customers served. These jumps correspond to the completion of service tasks by the agent, reflecting the system ability to process call efficiently. This metric is crucial for understanding how well the system handles customer demand and how quickly it resolves customer issues. It shows us not only the throughout of the call center but also how our model performs in ensuring timely service and customer satisfaction. This dataset is derived from PwC, which focuses on optimizing call center operations by improving call routing and agent performance. It provides valuable data for analyzing and refining the MDP model. Please note that this is a slightly modified version of original PwC dataset. In our version, we have made adjustment to simplify the call center operations. Specifically, the dataset now consider only two agents, one of which is capable of handling all topics, while other specializes in specific topics. This modifications allows us to test and optimize routing strategies that dynamically allocate calls based on agent expertise and availability. The key feature in this dataset include a call ID, a unique identifier for each call, and then agent ID, which identifies handle agent handle each cell, and then call duration, uh, time taken to handle each calls, and then queue length, which is a number of waiting calls, and then service level, which is the percentage of calls answered within a specified time of frame, and then customer satisfaction, that is the rating given by customers on a scale from 1 to 5. By analyzing this dataset, we can optimize decision making, improve call routing, and then ensure better overall call center performance. As we move forward, one of the most exciting steps in our project is integrating possible policy optimization or PPO into our system. Up until now, we have used Markov decision process modeling to optimize the call center routing process. While this method has been effective, one limitation is that MDP are generally static. Once the model is trained, it doesn't adapt to dynamic or real-time changes in the environment. This is where proximal optimization becomes essential. PPO is a reinforcement learning algorithm designed to improve policies by adjusting them based on real-time feedback. Unlike MDPO, unlike MDP, PPO can continuously learn and adapt by receiving new data, making it perfect for real-time optimization in systems like ours. With access to real-world dataset, we now have the perfect opportunity to validate the assumptions we've made about call center operations and optimizing call routing in a dynamic environment. By implementing PPO, we will be able to adjust call routing policies on the fly, ensuring the system can respond to changing conditions, whether that's an increase in call volume, varying customer satisfaction level, or agents availability. This continuous adjustment will help us fine-tune our model, ensuring that it always operates at peak efficiency. As condition evolves in the call center, PPO allows our model to adapt and improve, making sure we are providing the best service possible in a real-world, ever-changing environment. Ultimately, PPO will enhance our decision-making process, giving us the ability to improve system performance in a real time and ensuring optimal results across all situations. While the Markov decision process MDP modeling demonstrated great results in optimizing call center operations, its true values lies in its real-world application. By dynamically adjusting call routing based on real-time data, we can effectively reduce waiting times and maximize agent utilization, which leads to significantly improvement in customer satisfaction. And the model allows us to predict and adjust to peak call times, optimizing agent assignments, and make operational decision in real time. For call centers, this could mean an immediate reduction in customers' complaints, faster resolution times, and better overall service. With this model, we bring an AI-driven solution to optimize human resources, increase productivity, and ultimately deliver a better customer experience. The future of call center optimization will heavily rely on AI-powered solutions, and we are taking a significant step towards that with the integration of proximal policy optimization. Unlike traditional approach, PPO will allow us to adapt dynamically to real-time data, continuously improving the model as it learns from ongoing experiences. By adjusting call routing policies in real-time data, PPO will enhance our system ability to handle new customer patterns, seasonal demands, and varying workloads. Over time, this means that our model will keep improving and fine-tuning itself to ensure peak performance in the ever-changing call center environment. In conclusion, our work demonstrates that Markov decision process provides a robust solution to optimizing call center operation. By dynamically adjusting call routing and maximizing agent utilization, we were able to reduce customer waiting times and improve overall efficiency. Through real-time simulation, we have seen how our model performs in realistic setting, offering valuable insight into performance metrics like queue length and server utilization. Looking ahead, we plan to implement proximal policy optimization (PPO) to further enhance the model's ability to adapt real-time data. This step will ensure that the system continuously improves and remains responsive to changing conditions in the call center. And the final goal is to apply this model to real-world data for validation and fine-tuning, ensuring it offers practical, scalable solution for call centers in the future. That concludes the presentation of my research on optimizing call center operations using Markov decision process. Thank you for your attention and time. If you have any questions or would like to discuss any aspect of this project further, feel free to reach out on my GitHub repo or in the comment section below the video. I look forward to hearing your feedback. Have a great day.